We are living in the era of artificial intelligence. AI is ubiquitous. It's the topic of every conversation. But what exactly is the true nature of intelligence? For a billion years ago, single-celled life emerged. Through endless trial and error, DNA acted like a pre-trained model, eventually giving rise to the first central brains. From there, evolution accelerated. Species rapidly branched out, and by 310,000 years ago, Homo sapiens arrived. Then, 70,000 years ago, language sparked a monumental leap. Human curiosity ignited, fueling an explosion of science and industry. Fast forward to the 1940s, the dawn of AI. After our own relentless cycles of trial and error, we now have machines solving highly complex problems. But is this approach truly enough? While AI is our latest leap, our training methods are a step backward. We're reverting to primitive trial and error, burning thousands of GPUs to cram data into opaque black boxes. As AI pioneer Yann LeCun warns, we're not going to get to human-level AI by just scaling up LLMs. What we truly need is a transparent, white box AI, optimized through rigorous math. But before we can build that, we must first understand the true nature of intelligence. In its raw form, high-dimensional data looks entirely chaotic and random. But there is a hidden truth. Meaningful data actually lives on a simpler, low-dimensional manifold. By projecting our points onto this structure, we strip away the ambient noise. This is the principle of parsimony. Learning is, at its core, simply denoising. So, how do we mathematically uncover this structure? The answer lies in the principle of maximal coding rate reduction. First, we compress. We pack data from the same category tightly together, minimizing their local volume. Then we contrast. We push these different categories as far apart as possible, maximizing the total spatial spread. Compress within, contrast between. This objective gives us an optimal, white box representation. In the Crate framework, a deep neural network is no longer a black box of random weights. Each layer is actually a structured, mathematical step, an unrolled optimization process designed to compress data. IT uses gradient descent to minimize information loss, unfolding layer by layer to reach the most efficient representation of reality. Most modern AI models operate in an open loop. They process information in one direction, from input to output, without real-time correction. But biological intelligence is a closed-loop system. The brain doesn't just react. It constantly predicts what will happen next. That's why comparing its predictions with reality, it uses the error signal to update its internal world. This is the essence of self-improving intelligence. What exactly is true intelligence? It is the ability to self-correct and improve. Simply put, knowledge is the integral, the accumulated data. Intelligence is the derivative, the rate of adaptation. An AI holding all of Earth's data would be utterly lost on Mars. Compare GPT-4 to a newborn. GPT-4 has a massive database, but it cannot generate genuinely new knowledge. A baby starts with almost nothing, yet possesses the true intelligence to adapt and eventually contribute a delta of entirely new knowledge. All intelligent systems encode knowledge. Evolution used passive trial and error, but human science sparked active, logical deduction. This active logic was the true 1956 vision for AI. Yet, today's models only rely on passive pattern matching. It simulates primitive animal instincts, not human reasoning. We aren't building true intelligence, just a massive memory bank. If today's models aren't truly intelligent, then how do we test for it? For decades, we have relied on the Turing test. But this test has a fundamental scientific flaw. Who exactly is the judge? And more importantly, what specific questions should be asked to scientifically separate a machine from a human mind? To find the answer, we must look back at what pioneers asked 80 years ago. First, the Wiener test. Can the system actually self-learn and correct its own internal errors without outside intervention? Second, the Popper test. Can the system proactively hypothesize something and then mathematically check if its assumptions are self-consistent or if the theory aligns with real-world observations? If it cannot do these things, it is not true intelligence. The reality is, we have barely scratched the surface of machine intelligence, and along the way, we have forgotten a lot of valuable lessons established decades ago. So, how do we build systems with true intelligence? Let's bring it all together. All intelligence, fundamentally, is going after something parsimonious. Whether it is the laws of physics, the structure of our memory, or the languages we speak, they are all highly structured, low-dimensional rules hidden within a chaotic, high-dimensional world. The universal mathematical mechanism to learn these rules is compression. Intelligence forces raw data through a bottleneck, clustering similarities and contrasting differences to maximize the information gain about the world. But how do we know if our compressed memory is correct? We must use it. We use the memory to predict the future, and we check if our estimation is consistent with our actual observations. We do this either externally against the real world or internally to ensure that the memory becomes increasingly self-consistent and self-complete. This is not just machine learning. This is the ultimate pursuit of the nature of intelligence.